Hello everyone and welcome back to this next lecture in the machine simulation lecture series, and this is where we had left off last time, where we had simulated a current source according to a reference. To be more precise, let's go over to our editor, and we had set a reference that we wish to draw as a load current of 10 sin omega t, and we found from our simulation that we had indeed got this result, right? So we now are able to emulate a load that will draw a particular current which we are setting from a certain reference. So in this lecture I'm going to expand on this a little and try to bring in some more details besides just this very simple reference that we have set. So let's go back here, and as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses which you can access on my website, that is pythonpowerelectronics.com. So go over to the button Learn, and this is where the list of all my courses are. So the very first course I have is Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. And this is hosted on the website Udemy. You can click on this button. The next course is for signal processing, and this is how you can design filters and analyze filters specifically for power electronic applications using Python and the signal package within SciPy. So again, this is hosted on Udemy. You can click on this button to check it out. The next course is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can simulate magnetic components such as inductors, coupled inductors, and transformers using Python and Python Power Electronics. Again, hosted on the website Udemy. The latest course I have is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can design, analyze, and implement controllers using Python for power electronic applications. So in this I have used the Python control package, which is specifically suited for designing and analyzing controllers using Python. Again, hosted on the website Udemy. And the very latest course I have is a free course called Why Specialize in Power Electronics, and this is mainly targeted towards young undergraduates or even those who are not specifically experts in power electronics, to talk about the challenges and opportunities available in the power electronics domain. So the link for this page is provided in the description for this video. If you want to know more about these courses, check out the link in the description for this video. So with this, I'll get back to the lecture. So as I said, we will add some more details. So let's go over to our circuit, and this is what we have. This is the current source representation. So what I said, as usual, the current source is a controlled voltage source in series with a variable resistance, right? And we are adjusting this control voltage source with respect to the voltage that we are measuring across these terminals in such a way that we are going to draw a certain current. That's how it works. So here, let me make some comments, and as I said, I probably put everything together, and let me put a comment here saying this is the final implementation. So I'm just going to write a comment here saying final implementation of the current source, right? So here, this is our load model, which is at present quite simple. This is just, we are setting the load model such that the reference, the current required, the desired current rather, is just a sinusoid. That's it. Now in this lecture, I'm going to add some more details to it. So when I mean some more details, let's see what I have. The simplest thing which we can do, if we go over to this thing, is we had initially tried to simulate an RL load. That means a resistive inductive load. So if we were to emulate an RL load as this current source, right, what we would need to do is to solve the equations related to the resistance and inductance. That's what we would have to do. The reason why this would be interesting is that going further, we can use a similar strategy to even emulate an electrical machine like an induction motor or a synchronous motor, right? So let's come back here to our editor and let's make some changes. So the first thing I'm going to say is, let me put some comment here and let me say load parameters. So I'm going to say RL, which is the resistance of the load, is, let's say, 100 ohm. Put a comment saying this is ohm, and let's say LL, which is the inductance of the load, is let's say 0.3, and this is Henry. And the reason why I'm choosing it as 0.3 is because this will be multiplied by omega, which is 314.1. So if 314.1 is multiplied by 0.3, you get something very close to 100. So this is like a kind of a load where the resistance and the inductance are almost equal. It does not have to be, you can play around with these values, but just as an example. So now what would I have to do? If I want to emulate this, right? If I want to emulate this, simply speaking, the equation would be something of this sort. So let me write the load equation. I would say V measured minus RL R underscore L multiplied by, let's say, IREF multiplied by LL multiplied by d by dt of RIS. So I'm going to say d IREF divided by dt is equal to 0. Right? This is simple Kirchhoff's voltage law. Only thing here is, because I am saying that this is an RL load, I must take into account the L di by dt that is produced because of the inductance. Right? I can't just say omega into L into I, because that is not the dynamical equation. We are now trying to solve a dynamical equation so that we get an accurate representation of the load. Now, in such a case, we have now a differential equation. Now, when you have such a differential equation, the way to solve this is, you would take this to one side. So I'm just going to take it over. Right? Since it is a negative sign, I'm just taking it over to the other side, and I'll copy this back here. Right? So I'm copying V measured minus RL into IREF. Now you might think there's IREF on both sides, but here is where I'll talk about how you solve it as a discrete system. So again, we just have to say di by dt is equal to this entire quantity, except that now we are dividing it by LL. So we're dividing it by the inductance. So we now have an equation for the di by dt. Quite obviously, when you have such an equation for the di by dt, if I want IREF, all I have to do is integrate it. Right? And integration here is pretty simple, which means that if I want IREF at a particular sample, right, then in that case, I will be taking this diref by dt at that sample, multiplying it by dt, right? And this gives me diref, right? Because I am taking diref, this derivative, I am multiplying it by the time instant at which this control file is running, which we have already set here. Yeah, which we've set here. I mean, this is just a comment, so it doesn't matter. Which we've set here. And this will give us diref. Now, diref is not what we want as the actual current. This is the change in current, which means this change in current will have to be added to IREF n-1, which is the previous sample of the current. So if we expand this further, I'm just going to copy it to reduce the amount of typing I have to do. If I have to reduce this, and I'm going to get rid of this here and bring in this equation, this is the equation for di by dt. The only thing is this equation has the IREF, and we have not calculated the nth value yet. The nth value is the present sample of our simulation, right? So which means we haven't calculated that yet. So I'll use here the previous sample of current. This is our equation for finding out the reference current when our load is an resistive inductive load, right? So here all I have to do is, if I want to use this, I'm going to take this, copy it, and put it here, right? So I'm just going to comment this out. Now here there is something which we need to know, which is more simulation specific. right? I am using this as the nth sample in the n minus 1 sample. Okay, this is what I'm using in order to perform my mathematical model. But if we go back to our web browser, we might have to go back to the previous page where we look at edit control, configure control. We look at the static variables. We see that iref has been defined as a static variable. What that means is the value of iref is stored between every iteration at which this control file is calculated. So this variable has memory. So which means that if I remove this and I remove these subscripts, what I am referring to on the right hand side are the older values of the reference current. Right? What I'm referring to on the right hand side are the older values of the reference current. I'm calculating this and I'm evaluating it and setting it to the latest value of the reference current. So this is my new mathematical model for this RL load, right? So now that we've done this, let us go over and run the simulation and see what we get. We have almost everything. We don't have to change this because these are constants, right? If they are not constants, we would have to calculate them, and later on we might have to calculate, but for now we can leave it as it is. So let's go to the web browser, go back to the main page, go to view output, and let us click on run. It says simulation is running, but always go to the command line and make sure there is no error, and there is an error, right? So you see I made a mistake with respect to the variable. So let's come back, stop this value, and let's go back to the editor, and we see that we've actually chosen the wrong variable. We have set the measured value, that is this voltmeter, we have assigned it to the variable vTerminal, but we are using it as vMeasured. vMeasured doesn't exist, and that's what's happening. It's complaining, saying I don't know what this variable is. So let me go and just paste it here as well, so that I just remove any confusion, right? So that's it, I've removed vTerminal. So now we are saying that iref is with respect to vTerminal, not vMeasured. So let's go and see if we have gotten rid of our error. And let's go back to command line, and now you see there is no error, right? These errors are from before. What's important, you see the latest command line says all okay, right? There is no error here. So which means the simulation is running. So now that the simulation is running, let me go over again to the file browser and let me save this also. I don't actually have to, but let's save this. So I have the first one, which is basically the current when there was absolutely no voltage generated, and the second one was when I was generating the current according to a sinusoidal reference. Now let's see what we get when we try to simulate this RL load. So I'm going to click on plot, go back to the browser, interestingly there seems to be a bug, because let me go to the command line. There could be a bug in matplotlib, could be any reason. Let me try it again. Yeah, I mean, I don't know whether the problem was with matplotlib or whether it was something else. It's hard to know, right? But anyway, these bugs do happen. Any software has bugs, and that probably was a bug with matplotlib. So anyway, we now have the latest current, and here too there is another bug, because apparently it has plotted it twice. Let me delete it completely and plot it again. I don't know whether I clicked double or whether it was something else. I can't understand. Let me go to the file browser. Very interesting. It's just adding plot after plot. I'll have to check it out. I don't really know why this should happen, because we are generating a new plot. So anyway, coming to this, you see here that it seems orange. Let me actually shut down this. plot it again. And it's just adding one after the other. I don't really know what's happening. Let me go. I'm going to use the dashboard. Is it something to do with the mouse? Oh wow. Okay, this is something I'll have to check it out. I think it's something to do with Python because it is adding plot after plot and I don't know why. But I suppose another option is I just delete it. Let me just do that. I will delete it. Add plot. Current plot is good enough. Start the plot. It's not really a deal breaker, but it bothers when you have several plots superimposed because now you have thicker lines, right? Let's hope finally I have a simple plot. This is something else. I think this is something to do with the operating system. I can't understand it. But what's important to understand is even though it looks messy, we now have an RL load emulation. This is emulating an RL load. Now this RL load, if you really compare, it has exactly the same dynamics as would happen with a resistive inductive combination. Right? It has an initial transient. The reason is because there's an inductance. When you turn on a voltage with a circuit and an inductance, there will be a transient, and this initial different peak indicates that is the case. Let us zoom in between 0 and 0.1. So now you see this is a pure sinusoid, and it also appears to be a sinusoid of 50 Hz frequency. So in all those aspects, we have generated a perfectly RL load. The only difference is now our mathematical model is a little more involved. We are not setting a reference which is just a sinusoid, but rather we are calculating a current with respect to the terminal voltage and with respect to certain other dynamics that we are including with respect to the load. The only thing is the load is still something which is very basic, which is an inductance and a resistance. In the later lectures, we are going to add in more dynamics where we are going to actually emulate an induction machine or a synchronous machine or several other different types of machines using this similar concept. That is, we are going to include a load model. We're going to generate a reference current that we want that this machine is going to draw, and this reference current is what is going to be set by calculating this voltage of the control voltage source. This is the process that we are going to follow. So for now, let me quickly go and close this down. The next thing which we are going to look at is, now that we have this, we are going to examine a couple of other issues before we go on to actual machine simulation. The one thing, as I already said, is the series resistance. The series resistance is something that I have set to be 100 ohms. The reason why it has been set to 100 ohms is because this has been set in the control file itself. Right? This has been set to the control file as the variable resistance has been given this initial value, and I have not changed it in the control code. Now it seems to be working, and this is working because with this particular system it is acceptable. This value of 100 ohms is acceptable. However, to set such a value arbitrarily is not advisable. This variable resistor, even though it seems like it plays no role at all, can actually impact the stability of this current source. And depending on the stability of the current source, your entire load model will be affected by this one resistance itself. Right? Now, this I'm going to talk about in the next lecture, as this lecture has already gotten pretty long. In the next lecture, we will talk about how we should choose this series resistance, what are the impacts of choosing different types of series resistance, and why this is important in a simulation of an electrical machine. So with this, I'm going to end this lecture. If you have any doubts about what I did, please do post either in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next lecture, which will be next week. Thank you so much and see you soon. Goodbye for now.